Technology has greatly reduced the efficiency of buildings. It is time to look for solutions from the ancient past. It's been claimed that technology is the answer to the climate crisis, by eventually separating economic growth from its effects on the environment through improving energy efficiency. The argument runs: better technology promises to prevent catastrophic global warming. But among the many things that this argument fails to consider is the reality that new technology has often encouraged extravagant forms of consumption, from private cars and planes to kitchens full of appliances and air conditioning in countries with mild climates. Technology has also caused what's called the rebound effect, where improving energy efficiency leads to cheaper energy and therefore higher rates of energy consumption. For example, buying a more fuel-efficient car will reduce your average fuel cost per trip and thus is likely to lead to more trips, taking away at least some of your anticipated energy savings. A similar trend appears in architecture, where advances in artificial cooling, heating, and computer-aided design have, rather than creating more efficient designs, actually introduced wasteful building styles. In my work, I call this phenomenon the architectural rebound effect. This effect becomes especially clear when we look at how building facades have evolved over the past 100 years. The Cité des Refuges residential building in Paris, designed by Swiss-French architect Le Corbusier in 1933, boasts one of the earliest examples of a facade made entirely out of glass, but with no windows or air conditioning. Its summer indoor temperatures reached up to 33 degrees Celsius, making it a notable failure in architecture. To fix this, the facade was fitted with external shading devices and about a third of its glass was made opaque. This strategy was mostly effective. Computer simulations have shown that the upgraded design reduced indoor summer temperatures to below 25 degrees Celsius. From the 1950s, fully glazed facades without shading devices began to dominate city skylines thanks to increasingly efficient and cheap air conditioning systems that allowed temperatures inside THESE buildings to be regulated. But these new glass boxes came with their own set of environmental problems. For instance, research has shown that office buildings built in Manhattan between 1965 and 1969 consumed twice as much energy per unit floor area than buildings erected between 1950 and 1954. One reason for this is probably the difference in the window-to-wall ratio between these groups of buildings. While the later buildings had a ratio between 53% and 72%, the earlier buildings' ratio sat between 23% to 32%. This means that more heat was allowed into and out of the former group of buildings during summer and winter, increasing their need for artificial cooling and heating. These problems with fully glazed facades still plague buildings today. Parametrically designed shading devices are often used as a solution. Unfortunately, these tend to block outdoor views for those working inside, while keeping the need for artificial light. Should we prevent architects from exercising their aesthetic freedom in designing these extravagant buildings that harm our planet? One solution could be to set a maximum limit on the amount of energy a building is allowed to consume. This would require architects to use passive design strategies, techniques that enable humans to live in challenging climates without expending unnecessary energy. For example, by the year 400 BC, Persians had devised an ingenious way to store ice during hot summer months using ice pits called yak-chi-chows. These were vaulted reservoirs with a height of up to 15 meters and a depth of approximately 6 meters. By allowing hot air to exit through an opening at the top of the reservoir and burying ice deep in the earth, the base of the yak-chi-chow and the ice inside would remain cold throughout the summer. An example from the modern era is the Inspector General of Police complex building in Gulbarga, India, which uses a wind tower fitted with water sprays to create a comfortable environment. In a hot and humid climate, droplets from the sprays absorb heat from incoming air, reducing the air's temperature by up to 13 degrees Celsius before it enters the building. It's vital to first decide how best to measure buildings' maximum energy limit. In current building energy rating schemes, energy use intensity is often used, which refers to the amount of energy consumed per unit of floor area. But a flaw of this metric is that it allows overly large, grandiose buildings to be certified as low energy. A more appropriate metric could focus on energy consumed in relation to the number of people using a building, in other words, a building's energy use per person. A possible objection is that this could result in boring buildings with no aesthetic Appeal. In this case, we could encourage architects to express their creativity through building structures that are not designed to house people and therefore would require little to no operational energy to run. This would considerably reduce the environmental impact of such architectural masterpieces. On average, 80% to 90% of a building's carbon emissions arise from operating it, not building it. What's more, many iconic buildings have failed to function as they were designed to. Mies van der Rohe's new National Gallery in Berlin suffered from cracking windows and heavy condensation, while Frank Gehry's Stata Center at the Massachusetts Institute of Technology has leaky roofs and excessive mold. These buildings have not been demolished, however, but left standing as examples of top-quality design. Perhaps if architects channeled their desire for daring aesthetic into sculpture-like structures rather than buildings designed for habitation, they could continue to keep pushing the limits of design without making the planet pay. Bashar al-Shaw is a PhD student in architecture at the University of Bath. This article is republished from the conversation under a Creative Commons license. Read the original article.